All right, so let's talk about today removable discontinuities or holes, okay, in a graph. Um, so what is a removable discontinuity? It's pretty much a a point of discontinuity. So continuity means like here, if I'm tracing a graph, let's say this is a graph of something, and then I have to lift and then start going again. Whenever I have to lift, that's a point of discontinuity. I'm continuous everywhere else because I could trace it just by with my pencil on the paper, but when I have to lift my pencil and then go again, that's now we're discontinuous there. So that's what it is. And so a hole or removable discontinuity is when you got just one little spot, one point, tiny point, where we have no value. We're undefined there. So how does that happen? And so let's talk about that real quick. How does that happen? The way it can happen is we have something like this. And normally what you do is like, well, where are my vertical asymptotes? Normally you do that. Where are my vertical asymptotes? Well, vertical asymptotes are where my denominator is 0. So we'd say, okay, well, let 3x squared plus 24x equal 0, and we'll solve it. Let's find those vertical asymptotes. So this is a polynomial equation, a quadratic equation. So we normally try to solve these by factoring. So I think this does factor. So I get 3x. I can factor out of both of these, greatest common factor. I get 3x times x plus 8. And therefore, I get that x is either 0 or x is negative 8 would be my two solutions. And so these would be my two vertical asymptotes. Now, however, if we're paying really close attention to the rules, they're only vertical asymptotes if they're not also zeros of the numerator. What if there's zeros of the numerator also? Because zeros of the numerator are y-intercepts, usually, right? But what if you have a 0 that's the same on numerator and denominator? What would that mean? So let's take a look, and let's factor. Now this factors very easily. X squared minus 64. We know what that is. X squared minus 64 is x minus 8 times x plus 8. So what you notice is both the numerator and denominator have a factor of x plus 8. Okay, so that means where we were undefined, we're undefined these because these make the denominator 0. That means those are places we're undefined. That's still true. However, everywhere else, these two factors don't make a difference, right? So let's play around with this. Well, f of x equals, I'll rewrite it factored, x minus 8 times x plus 8. And the denominator is 3x times x plus 8. And so what we find is they don't matter because these would cancel out. X plus 8 over x plus 8 always equals 1, except when x is negative 8. Then we're undefined. So in other words, this is the same as x minus 8 over 3x times x plus 8 over x plus 8. Well, that's just 1, right? For the most part. So that's what we get is our graph will look exactly like x minus 8 over 3x. It's the exact same thing. This here, I gotta have a little caveat here. When I did this, we gotta say except when x equals negative 8. We can't forget that f of x did include this. And so these are equivalent. what I started with and this are the same thing except for this one point. And that's why we call it a removable discontinuity. So let's take a look at the graph. All right. Let's see here. Okay, let's take a look at the graph. Here I have our original function f of x equals x squared minus 64 over 3x squared plus 24x. There it is, right? And remember, I can write the asymptotes. We can find those real quick. Asymptotes of f. And we get 2, y equals a third, and x equals 0. And I can find the holes. This is really neat. This I didn't put in my last video, but you can actually type in removable discontinuity and put in f. I'll show you. Look at that. There's a hole. Where's the hole? At -8. -8 comma 2/3. And with a point, actually, I think this would work. Insert text. Can we put in a point? We can. So this point is A. So if you need to, an easy way to figure out what that is as a fraction, there it is. So, okay, so -8 2/3. Also, what we can do is over here, we know at -8, well, I put it over there, funny enough. Oh, that's funny. That's kind of neat. But anyway, there it is. There's my hole, and we can also do the show value. It'll show it that way. So there's a hole in our graph. Now, I said these are the same, right? This is the same as this. So let's see if that's really true. It should be. So let's go g of x equals x minus 8 over, and before I finish too, how do we find these points on our own? We know the x value. How would you find the y value of the point without using the calculator? There's an easy way to do that. So think about that for a second. We're going to do that right now. So g of 8, x over 8 over 3x. Hit enter. Look at that. The orange overlaps the green. My orange function. G is the exact same as f, except g does not have a hole here. What's showing A, but g does not have a hole here. No holes there. And I can type in the function there too again. But f, if we do f, does have a hole. Okay? So it is exactly the same. That's what we'd expect. So how do I find the hole? Well, that's easy. Okay? Since I know that this function, x minus 8 over 3x, is equivalent to what I started with, except at this point, where's that hole going to be? Well, just plug in x equals -8 into here. So, it'd be like f of -8 is really undefined, right? It's really undefined, but what if it weren't? Where would it be? Well, it'd be at -8 minus 8, right? So I'm plugging in -8, so over 3 times -8. So we get -16 over -24. Positive over a negative over negative is positive, so those cancel. These are both divisible by 8. 16 divided by 8 is 2. 24 divided by 8 is 3. There's my 2/3. So where's our hole? Or our removable discontinuity? I like removable discontinuity. It's right there at -8 comma 2/3. And that's how you do these. Very easy. At -8 comma 2/3. All right. There you go. So that's how we do them. Thanks for watching. Until next time, enjoy doing math.